So far we've looked at the roots of quadratics and cubics. Now we're going to look at the roots of what's called a quartic. So a quartic is a polynomial where the highest power of the variable is 4. So we've got a z to the power of 4, z to the power of 3, z squared, a z and a constant term. Another way of describing a quartic would be to say that this is a polynomial of degree 4. Or another way of saying that, you might hear the word order 4. So a cubic, for example, is a polynomial of degree 3, and a quadratic is a polynomial of degree 2. So let's look at the cases of the roots of a polynomial of degree 4. Well, a polynomial of degree 4 has no more than 4 distinct roots. So the possibilities are all four of the roots are real, and within that you could have some repeated roots, just like you would do with a cubic. If you've got a non-real root, then as long as the coefficients, so as long as A, B, C and D are real, then you're going to have a complex conjugate pair. So one possibility would be that 2 of the roots are real. So for example, you could have -1 and 2. And then the other 2 roots are made from a complex conjugate pair. So you could have 5 minus 3i and 5 plus 3i, for example. That's one case, 2 real and 2 complex. The other possibility is that they're all complex, they're all non-real. So an example of that would be you've got 3 plus 7i, 3 minus 7i, and then another complex conjugate pair like 5 minus 3i and 5 plus 3i. Now notice that it's impossible to have 3 different complex conjugates, 3 different complex roots. That's because, or 3 pairs of roots, because then you'd have 6 roots in total. So for example, I couldn't cross this one out and say that actually one of the other roots is another complex number, like 8 plus I. The problem with that is we know that 5 plus 3i has to be a root because it's a conjugate pair, and we also know that 8 minus I has to be a root. So that would lead us to have 6 different roots, but we know that it can't have more than 4 different roots, so that's not possible. So let's have a look at example 11 then. So we've got a quartic and we're told that 3 plus I is a root, and we're asked to solve the equation completely. So the first thing that we do is we realise that because the coefficients 2, minus 3, minus 39, 120 and minus 50 are real, then we know that the complex conjugate 3 minus I is also a root. Okay. Well, because of that, we know some factors of this quartic. We're basically going to try and factorise this quartic. We know that z minus 3 minus I is a factor, and also z minus 3 minus I, 3 plus I is a factor too. So that means that we can write this quartic as these 2 factors multiplied together. And then we're going to have to multiply it by another polynomial. And so far we've got z times z, and we want a z to the power of 4 at the start. So we know that this must be a polynomial of degree 2. We basically need a z squared at the start here. So we can times it by this quadratic to get the quartic. And notice that if you're not sure why you know that these are factors, just try it. If you substitute in this root 3 minus I into these values of z here, then you can see that this bracket here is going to go to 0, because you're going to have 3 minus I and then minus 3 minus I, which is 0. Similarly, if you substitute in 3 plus I into this bracket, then you get 0. So you know that these two must be factors. They must be factors of this quartic. So let's multiply out these two brackets to try and find out what quadratic you get when you multiply these two factors together. So I'm going to do z times z, z squared, and then z times by this thing here to get minus z 3 plus I, and then minus z 3 minus I, and then plus 3 minus I, 3 plus I, and then we're going to times that by our quadratic, which we don't know. And next, let's simplify what's inside the square bracket. Let's expand it a little bit more. And notice that when I do minus I times I, I'm going to leave that as minus I squared for now, just so I don't make any mistakes when I simplify I squared. So now let's simplify what's inside the square bracket. So I've noticed that inside the square bracket we've got minus zi and plus zi, so they cancel. And we've got minus 3i and plus 3i, so they cancel. So we've got z squared, we've got minus 6z if we collect together the z terms. And now I'm going to say that minus I squared, because I squared is minus 1, we're going to have minus minus 1, which is plus 1. And then add on the 9, which is 10. And then we've got times by az squared plus bz plus c. So there I've used the fact that I squared is equal to minus 1. So there's a few methods for finding out what this quadratic is. If you're confident with dividing polynomials, then please feel free to skip forward and see if you can finish off the example. I'm going to go through two different methods of finding out what this quadratic is. So the first method that I'll do is long division. And obviously you can choose which method you prefer or which method you've used before. So we're going to do this quartic divided by this quadratic in order to find out what this quadratic is. So we're going to ask ourselves, what do you have to times z squared by to get 2z to the power of 4? That's 2z squared. And then we're going to times everything, 2z squared by everything on the outside. So we're going to have 2z to the power of 4 minus 12z cubed and plus 20z squared. And really we've got plus 0z and plus 0. You can write that if you want to, just to keep the columns neatly lined up. And then we're going to do the top line, take away the bottom line. So 2z to the power of 4 take away 2z to the power of 4 is 0z to the power of 4. This take away this gives us minus 3 minus minus 12, which is 9z cubed. Minus 39z squared minus 20z squared is minus 59z squared. And then 120z minus 0z is plus 120. And minus 50 take away 0 is minus 50. Okay, so next we're going to ask ourselves, what do you need to times z squared by to get 9z to the power of 3? That's plus 9z. So now we're going to times 9z by everything on the outside and write it underneath. Okay, and then let's do top line take away bottom line again. So we're going to have 0z cubed minus 59z squared minus minus 54z squared is minus 5z squared. And then we're going to have 120z plus minus 90z, which is plus 30z, and minus 50 take away 0 is minus 50. And then repeat the process for one last time. What do you have to times z squared by to get minus 5z squared? That's minus 5. And then let's times minus 5 by everything on the outside. So minus 5z squared plus 30z and minus 50. And then we should just check if you do the top line take away the bottom line, you get a remainder of 0, which is good. And that means that this quadratic goes perfectly into the quartic. Okay, next let's do grid method. So with grid method, we're saying, well, we want to do this quadratic times by this unknown quadratic to end up with this quartic. So let's say this quadratic multiplied by this unknown quadratic. So az squared plus bz plus c. And if we do that, inside the grid, we want to end up with the quartic that we are looking for. So the thing to realise here is our z to the power 4 term is going to come from this box here. That's the only way of getting z to the power 4 when we do this grid method. Our z to the power of 3 term is going to come from these boxes here. So that's going to give us our z to the power of 3. It's like diagonals. Our z squared terms are going to come from this box here. It's going to give us z squared. This box here is going to give us z squared. And this box here is going to give us z squared. And similarly, these blue boxes are going to give us the z terms, and this final box is going to give us the constant term. So let's work out what we need to put in at the top here, what this quadratic needs to be. So when we multiply to get the z to the power 4 term, we want 2z to the power of 4. So we know that we must have 2z here, and that's going to give us 2z to the power of 4. Let's fill in this first column then. So 2z squared times minus 6z is minus 12z cubed. And 2z squared times 10 is 20z squared. And then with these yellow boxes, we're going to have our z cubed terms. We want minus 3z cubed, so we're going to have to add on 9z cubed to the minus 12 in order to get minus 3z cubed. So that must mean that we need a 9z there, plus 9z, to make sure that we get 9z cubed in that box. Let's complete the second column. So we're going to have minus 54z squared, and we're going to have plus 90z. Well, these purple boxes need to add together to give us minus 39z squared. So we need a minus 5z squared to make sure that happens. So we must have minus 5 there. And then we can fill in the last column to make sure that the rest of the boxes give us the 120z and the minus 50. So the z terms work, we'll have 120z and we'll have minus 50. So that works out well. Okay, so our last step is to say that, well, we know that this can be written as a quartic can be written as this quadratic, which we already know, multiplied by this quadratic here. And we want to solve it equal to 0. Well, we already know the roots of this quadratic here. The two roots we found already, because we had already factorised that. 3 plus I and 3 minus I. So there's no point solving that quadratic again equal to 0. Let's solve this quadratic equal to 0 though. So we could have 2z squared plus 9z minus 5 equals 0. And then you can choose your favourite method for solving this quadratic. I'm going to use the quadratic formula. So we're going to have z equals minus 9 plus or minus the square root of 9 squared minus 4ac all over 2a. So we're going to have z equals minus 9 plus or minus the square root of 121 all over 4. Now notice that we haven't got a complex number here because we're not square rooting a negative number. So that means that this quadratic is going to have these two complex roots, or non-real roots, and then two real roots. So we're going to have z equals a half, or z equals minus 5. So it's a good idea just at the end, just to say what are the roots. So the roots are 3 plus I, 3 minus I, which probably say z equals a half, or minus 5.